problem is totally good review for you for your test tomorrow, by the way.
Okay.
Just the first part, the graphing part. So we need to graph this before we can decide where it's discontinuous. And that's the part Gracie's gonna learn.
Gracie, do the graphing part for us.
Greasy cannot.
Oh.
Gracie can. Okay. When we graph piecewise functions, which was like this question on your paper. What do we have to do?
Graph it.
We do a T-chart for each piece. So the first piece, I'm going to start at -3. Now it didn't have an equal to. I still have to plug in the -3. What will I put then?
An open circle.
Okay, and then I need x's less than that. So maybe like -4, -5. And I am plugging them into my equation. Okay, so if you put in a -3, we get -9 plus 12 minus 4. And we get what? -1. So -3, -1 is open. Okay, if we put in the -4, we get a -16 plus 16 minus 4. -4. Are you ready to take that quiz? If you have a non-graphing actually it won't make a difference on this. Okay. And if we put in -5, we get -25 plus 20 minus 4, which is -9. Okay. So it looks like this. Now we do the second piece. So we make a new T-chart for that piece. We have to put in -3. Will this one be open or closed?
Close.
Closed. And then we need things bigger than that. So maybe a -2 and a -1. So if we put in -3, -6 plus 1, -5. If we put in -2, -3, so it started here, it's going this way. Keep in mind, these are functions, so it should pass a vertical line test at the end. And it does. So we're just using the graph to kind of confirm what we were talking about yesterday. If we hadn't graphed it, where would we have been concerned about a discontinuity? At -3, because that was the breaking point. Is it in fact discontinuous at -3?
Yes.
Yes. So we are asked to determine if it's continuous. If not, tell the location of the discontinuity. So this is discontinuous at x equals -3. And classify it. What type of discontinuity is that? Jump. And I told you jump typically happens on a piecewise where one piece is a less than and one is a greater than. So we're going to jump from one to the next. All right. Let's look at number 12 together, and then I'm going to have you guys try the next two on your own. So number 12. X over 2. When x is not 3. And 2 when x is 3.
Totally got excited about a line, but it wasn't even real.
Okay, so not equal to 3. Does that mean on my T-chart I don't have to plug in 3?
No. You still have to do
We still do, but when we put in 3, it would be open. And then you want everything else. So smaller, bigger, everything. Okay, so if I put in 1, I get -1/2. 2 gives me -1. 3 gives me -3/2. 4, -2. 5, So we're seeing just a line. 1, negative 1 half. 2, negative 1. 3, negative 3 halves is open. 4, negative 2. So we have a line with a hole in the middle. Which I told you is what happens when you have a piecewise with an equal and a not equal. The second piece, 2 when x equals 3. How do we graph that? Just a dot. So when x is 3, the y is 2. Okay, so where is this discontinuous? X equals 3. What type is that? Okay, so here's what I want you to do. I want you guys to graph 13 and 14, but why don't you like work with each other so you can check yourself. So group of 2 or 3 or 4, I don't really care, but check yourself. So graph them, yeah, or whole class effort, whatever you want. Somebody wants to come up to the board and do it.
Ooh.
All right, 13, you had a parabola with a hole in the middle. Actually, you have the others.
Oh,
as well.
did I? Okay.
So where is this discontinuous?
Oh, it's at -1.
What type is it?
It's removable
And why was it removable and not jump?
because it's 1 point.
Yeah, because we had equal and not equal as our conditions. All right, the last problem. So if you factor, top we have x plus 2. The bottom, this would be x plus 2, x minus 1. What happens? When those cancel, that makes a hole in the graph. At the x would be -2, the y, if you put -2 into what's left, you get 1/3. So on my graph,
That'd be removable.
so we get -2, 1/3 is a hole. Okay, this one would have a vertical asymptote at +1. Horizontal asymptote turns out to be 0 because the degree on top is smaller. And so if you graphed it, it turns out to look like this. You could plug in some points to check that for sure. These are a long process to graph those, but we're kind of getting an idea. So we see we had 2 discontinuities. So it's discontinuous at x equals -2, but what type is that? At -2? Removable,
Yeah, it's not.
because it was a hole. And at x equals 1, it would be
Infinite.
infinite.
So it is.
So we had 2 types of discontinuity on that one.
I forget that you have to have that graph too.
How?
Yeah.
Well, in the next section, I'll show you the calculus way of doing it. In college algebra, we had rules that told us what they would be. But why don't you just hold that thought instead of me trying to reteach you to memorize rules? Tomorrow, I'll teach you how to do it for calculus. Yeah. All right. Last thing we need to cover, intermediate value theorem. We mentioned this in algebra. And it is very helpful. It tells us if you have a continuous function. What does it mean if it's continuous?
You don't ever, it never starts. You don't pick up on it.
We don't pick up a pencil. And we have like 2 x's, a and b. Okay? Then we use this most of the time with finding zeros. If this is continuous, and let's say when you put in A, you get a positive answer, when you put in B, you get a negative answer, then what has to happen somewhere between A and B? Has to hit the x-axis, it has to equal 0. So that's really where we used it. The key to that though, it only works if the function's continuous. Okay, if it were a piecewise function, would it have to be the case that it crossed 0? No. So, last 2 examples. If I want to show there is a root to the equation, that just means there's a solution. I want to show that somewhere this graph is equal to 0.
Grouping.
Okay, you could try grouping to factor
but it won't
nicely.
work.
Oh.
It doesn't work. No, I'm not that nice.
That's terrible.
Okay, but did I ask you to find out what the 0 was?
Yeah.
No, you just told us to prove that there is one.
I
Told you
Prove that there is
more than 0.
Okay, what do we know about this function?
It's gotta be
It
continuous.
equals
Yes,
0.
it is a polynomial,
Oh.
so it is continuous.
Oh, that's kind
Okay, Caitlin said to put in 0.
Yeah, but I say that now, but I take that back.
Well, let's go with it.
Okay.
If we plug in
It's
0,
gonna be wrong.
we get 0
-2.
minus 0 plus 0 minus 2, we get -2. So that means 0, -2 is point on my graph. Okay? If I could get another x value that gave me a positive answer, then would that show that somewhere it had to equal 0 between them?
10.
1.
1 would give me 4 minus 6 plus 3 minus 2. I think that's still negative. Let's try
4.
2.
Do 10.
You go for it, Carson. Okay, 2 cubed is 8 times 4 is 32 minus 4 times 6, 24. And we get 12. So, did that show it to me?
Mm-hmm.
Yeah. On these, you're not giving me a whole lot of detail. All we're showing is that it equals 0. So all of the work that I really need, you have to tell me it's a polynomial so it's continuous. Because if you don't tell me it's continuous, it doesn't work. We need to show that we can plug in two different x's and get a positive and a negative. And then you just say, by the intermediate value theorem, there must be a solution or a 0 or a root between 0 and 2. There is some x value between 0 and 2 that would make this thing equal 0. And I know that because it's continuous in the sign change. Alright, last example, and then you guys get work time. Assume f of 1 is equal to -5. So that's like a point. When x is 1, we get -5. F of 3 is equal to 5. When x is 3, we get +5. Does that mean there is a value between 1 and 3 that makes it equal 0?
Yes.
Is it continuous though?
Ooh, real tough question.
No. We don't know. The function is continuous. We had something like a piecewise, that may not be the case. So it could be, but I didn't give you enough information to know that for sure. All right. Homework today is a handout that should look extremely similar to those class examples we've been doing the past couple